I think last time we have considered about inverse function and mainly talked about many type of functions. So, but we have not talked about the last two pages, like the cancellation laws and how to use the in and some examples of the inverse function. So we'll first introduce these topics and then go to our main topic, which is how to compare the size of the sets and how to count in mathematics. So let's first view about what's the cancellation laws. So it defines as like f if f is a bijection, which means it is both surjective and injective. And in this case, like it has two properties. So first, if the bijection is on the left hand side, you can see um, here on the left hand side, and then composite with another function. Then if this is equal, then G is equal to H. And this is called left cancellation because we are canceled out the bijection function f on the left hand side. And if it's a right cancellation, then we are doing the f on the right hand side. And then if their composition with R and S, they are equal, then R is equal to S. So we're going to see some proof ideas about this too. So they are pretty similar. I would say the proof process is very similar, just like changing the composition into a form of like F, first do G, then do F, and then introduce the inverse functions definition into it, and then do the proof altogether in the end. So let's see the first proof, prove the left cancellation of the cancellation loss. So first, because F is a bijection, so by the bijection property, every bijection has an inverse function. So there exists a F inverse such that the inverse of F, um, then doing the F is Fx is equal to X for all X equal to in the domain of F. I would say this is due to the definition of an inverse function because they are taking the pre-image, they are taking the image of a function and return to its pre-image. So in this case, if we take the inverse function outside of f composite with g, this is f composite with g, just right in the in the original form. So what will happen? What happens is that the f inverse composite with f and g. This is uses the uh associative law, the associative law of function composition. And then it turns out to be gx because this one is just empty out for all of the x belongs to the domain of G. And just notice as here, the assumption is f composite with G is equal to f composite with H. So the domain of G must equal to domain of H because the domain of f composite with G is equal to G, and the composite of the domain of composite f with H is also equal to H. So domain H is equal to domain G. And this is for all of the X belong to domain G. And this property is also for all of the X belong to the domain H, which is also domain G by their equivalence. And this is pretty similar. This is exactly the same approach as you can see here. We just get a inverse because we know the inverse exists. Take it outside and then use the associative law, and it will turn to be hx. And because they are equal, and putting a composite function like on both sides, well, that doesn't change the function's reaction because they're just like they're just taking the form of because for example, if hg is equal to fh, then what happened is the range, the calculation out of like fg is this part and is equal to fh equal to fg. The range is the same, right? And if you take f inverse again, it will be a certain one because the input is already fixed. So this is theory we used here. So what we know is that they're equal for all of x belong to the domain of G. I think I write it wrong here. It should be in G, not F. Okay, because G is equal to domain F as not FH as well. So in this case, we can see Gx is equal to Gh, which is definitely correct. Because if it's not Gx equal to Hx, then, well, this is what we learned from here. And we do the cancellation here to reduce to this form. So we have already solved it. It's all of the x belong to here as well. Okay, so this is the first direction proving. And what about the second direction? The second direction is very similar. Just do the inverse at the end because the f is at the end. So if they are equal, then if you take the pre-image of f minus 1, which is equal to f inverse taken, this is exactly the law of the first one, because if you're doing taking the f inverse at first and then do this too. If they're the same, then let's say first there's a set, right? There's a set called maybe A and f minus 1. They will exactly turn into a set B. And because A is fixed, so there's only one opportunity for B. So B is fixed. And then you will take R composite with F to become some final set. And because C, for example, they are into C. And because we know B from B to C, this step is fixed. So this is fixed because RF is equal to SF. So what's going from A to B to C is exactly if you take F minus 1 doesn't affect it at all because it just brings the fixed domain for our function, which is defined here. So this is our logical process why the first equation is always true. Okay, and exactly as what we did before, just to separate out, because at here, the first function is f inverse. So the domain for this two function is both domain of f inverse. So for all of x belongs to the domain of f inverse, you do the associative law for the function composition, and you first calculate this out. And what this belongs to is, well, x taken by inverse x, which is inverse x, and then take the f, which is x again. So it's equal to rx, and this is sx. And this function means r is equal to s. Because this is a definition. This is a definition of a function. Their domain the same, and each value from the domain just takes you the same value in the codomain as well. So which means the two functions are the same. So proof is done. The right cancellation is also proved. Okay, so let's see one example of an inverse function. So the first function I want to show is like, for example, first define what R plus means. So it means like all of the number or all of the real number and the real number is greater or equal to 0. So this character always means like non-negative real numbers. And if you say 2 plus sign like that, that means like all the positive real numbers, because positive is at a greater positivity than non-negative. So this is our tradition to use the denotion here. So this is defined, B is defined as x greater or equal to 5, which is not very common in different questions. So it's defined as B, not a specific characters. We will not say it's 5 plus, or if it got designs like another function called like, how you say, let's see, n plus means x belong to R and x greater or equal to n, then this can be writing as 5 plus, right? But it doesn't exist in the tradition of math history. So we are using B. define the function from the non-negative real numbers to b. And one way of writing f, there's infinite many cases like we can define f that goes from this set to this set, but we define as x equal to x squared plus 5. So here, somebody will say, well, the x squared might not be 1-to-1, right? Because remember, shape is a U shape, and it takes two different x values to the same value. But in this case, let's consider it's defined as the non-negative number, so it can only be the right-hand side, which is bijective, so it must have an inverse function. So in this case, how can we find inverse function? The usual strategy we will use here is like, first you are like if the bijection is x go to fx, then finding the inverse of f as we want to find it here. It's just like solving x in terms of fx. So we get the function like that. So the first step we'll make is to solving for this variable x. So x squared is equal to fx minus 5, and s equal to this one. So, and then for the last step we usually do is to rewrite x as the inverse of x and fx as x. So we just solve it. It's equal to the root square of x minus 5. It is correct. So we can check it, like first like check the domain, whether all of the x taken from this set's domain, and first taken f, and then taken f minus 1, and the inverse f also goes to the positive number. So let's first consider the x transition. So first taking f, x becomes x squared plus 5, and now taking the inverse function, which is minus 5, right? And this becomes 5 minus 5, which is 0, is root square x squared, which is x. And in this case, x, because in this case it goes to 5, and at the least taken to 5, and now minus 5, which means it all goes to 0 again, which is the non-negative set. So this proves it is really the inverse function. Okay, so the last theorem I want to introduce is called inverse bijection theorem. It's very important because it's like a De Morgan's law in set and logical operations. So it's like, say, f goes from A to B, g goes from B to C, A f taken to B, and g takes B to C, takes to here, and then f first goes from f, then goes g's negative. Okay, so first taken f, then taken g is inverse. Oh well, let's suppose because the composition function is going from A to C, then its inverse might goes from the C to B and then to A, right? This is because inverse are usually taken, if it's taken A to C, then must taken C to A. So this might be our inverse. And maybe we'll first do a G inverse and do a F inverse. So this is G inverse and this is F inverse, which is actually makes sense. But how we can prove it? We can prove it by showing a very interesting case, because here, this is what we want to prove. And it's already shown the inverse of G composite with F is equal to F inverse composite with G inverse. In this case, we're just going to show this one, a composite with G, composite with F is equal to the identity is equal to the original set of A, and this is equal to the original set of C, and this is based on the finding of our previous theorem. So first, how to show this one? This is pretty easy. I would say it's pretty easy because it's very intuitive. Just use the associative law many times, like because this disappears, so we want to make it disappear. Okay, and what this disappeared into, G is taken from B to C. So so let's say G first take B and it turns to C, and C was taken by inverse of G, which should go to B again. So this is IB, which is exactly if after taking X of F, then it goes to B, right? And then times IB, which is also B, and B going back again, which is A. So this is the proof of the first one. And conversely, it's very similar. So I think you can just read it. It's not much different. It's just the same, but working with a different set. It's going from the set set A to set B. Here might be set B, set B, set A. Okay, okay. It's not very similar. It's not exactly the same, but very similar. So maybe we can go through it again. So first one to just to reduce this one. So we reduce this one into zero. No, not zero, into identity. And what's the identity that first take inverse of F, which is goes from B to A, and F A to B, so it's IB. And what's the inverse of G? Inverse of G was taken from like the B to inverse of G is taken from C to B. So it's B. And because it's IB, IB times the set B is also the function itself, which is G inverse. So now it becomes X taken from when X is taken by G inverse, which is go from set C to set B, and then do a G again, which is going from B to C. So it's IC. So these two cases we already proved this one. All right, so this is what's left over from the function. I'm gonna go to cardinality here. So by studying of the cardinality, we'll re-looking into the set. So the topic of cardinality is about learning to count numbers, especially when you have many elements in the set. You may want to ask how many elements in the set, and this is what we are doing. But you may think like count is very easy because from when you start your memory, you already have the ability to count. Like you can count how many people in the room, just count 1, 2, 3. And if you remove all of the people, then you are done with the number. Or how many floor of a building, just come from the first building, second building to maybe the top is 6th floor. So there's 6th floor in the building. So that's the count process. But why we want to study it? Because sometimes the counting might fail when the number becomes strange. So for example, if a hotel has some rooms and then the motel has some rooms, motel is different from hotel, but I prefer motel usually. So how can compare the hotel, which hotel or motel has more rooms? So we can do this one. Like for example, here is a hotel. This is hotel, and this is motel. And it has 1, 2, maybe I don't want to count here. And hotel has this many rooms. And we want to, what we will do to say which one has more rooms, we just connect a string with each 2 rooms. This is, we connect it, and we connect this 2, and we connect this 2. Okay, and what we find out is here is the motel has some room which is not connected, and hotel has all of the room being connected. So what it means here is like what a hotel or motel has more rooms is the one left with unpaired rooms, which is this one. So in this case, motel has more rooms, and we can prove by our common sense, like 4 is greater than 3. So this example, like our counting is correct by our common sense from society, from our lives. And there's only 2 cases remaining. Like if there, in this case, what if there's another room, the hotel, then this is connected with the motel room again. Then all of the rooms are paired, and in this case, we say they have the same number of rooms. All right. And another example of this one is consider a hotel with infinite many rooms. So in this case, the hotel becomes like that. So there's 1 room, 2 room, 3 room, 4 room, 5 room, 6 room, and it goes to many rooms, infinitely many. So in this case, our counting might not make sense because we say every person in a room is occupied, every room is occupied by 1 people. And there's 1 more people standing here and say, I want to live in this hotel as well. So one way to make sure like he can always get into it. So in this case, we say number of room is equal to people. Room is equal to people because each room is occupied with 1 people. But what about like the room remains same? Do it still equal to p plus 1 if the people increase 1? Yeah, it still makes sense because it's infinite many. So for all of the room, maybe this is very great room number. We can always put it into the next one. And this people go to this one, this people go to the previous one, and this people go to the previous one, and this people go to this one, this people go to this one. And you can say here, well, this room is now empty, so he can just reach the room here. Okay, so in this case, we say, well, R is actually equal to P plus 1. And here, R is equal to P, which is not very in a common sense because P plus 1 is not equal to P by our sense, but here it's the same. So our counting may have some problems, all right? So it's anti-intuitive with our knowledge of life. Why if we add 1 more people into the room and it still have the same people with the room, which is not very believable by most of the ordinary people. So here we want to introduce some methods of how to do this correctly, how to compare size set, the size of set which is infinitely large. If all of the set with the infinitely large are the same or they are different. So first definition we want to introduce is called cardinality. Cardinality is just the size of the set. So set A and set B are said to have the same cardinality or cardinal number if there exists a bijection function f going from A to B. So here A and B are equipotent sets denoted as this with this one, which is read as like A is equipotent to B. And we say A and B are in 1-to-1 correspondence. So why there exists a bijection is very important. It's because in the definition, we consider a set A, which has some elements into it, and B has some other elements into it. Then what a bijection means is like all of the elements, they are numbered and they can be paired. So in this case, this is not a bijection because it is not a surjection. There's a remaining 1 in the set B from set A. So if you want to, and we can see here I have 5 elements here, 4 elements, which doesn't have the same cardinality. But if you add 1, and this is connect to here, which means it's bijection right now, and they have the same cardinality. Or if A or had B, A has 1 more, and this has to go to some set which is not an injection or it is not a bijection. And in this case, it is again not with the same cardinality. So we want to show if there exists 1 bijection, as we just saw in the previous example, then they have the same cardinality. So so I would say the logic is if there exists not means for all of the function, because for all of function, which means like which is impossible because many functions they are connecting to some numbers of we can make an easy example here. So this is A going to B, and A has 3 elements, B has 3 elements, which have the same cardinality, right? But there also exists a bijection. a function which is not bijection, like this go to this one, and this goes to this one, and this goes to this one, then it is neither a surjection nor a bijection. But they still have the same cardinality. So their exist is very important, not means for all. There's no need for all to be true here. So then we say what is a negation of this statement is just to write a slash line here. So which means A and B has different cardinality. So let's say one's theorem. So the equivalence relation, which is also called like the same cardinality relation, is equivalence relation on S. If S is a collection of sets. So if you want to prove like some relation is an equivalence relation, we just show it to prove it in three different ways. First, reflexive, symmetric, and then we'll say it's transitive. So why is reflexive? Because the identity function A goes to A is always a bijection, because because A the codomain or range is the same as its domain, which means they have the same cardinality. So equivalence is reflexive, or if it's symmetric. So for all of the different sets A and B, if A is has the same cardinality as B, then there exists bijection from A to B. And because every bijection has inverse function, which is also bijective, so there exists an inverse of F going from B to A, which is also bijective. So in this case, B is have the same cardinality as A, which means it's symmetric. So the third example, we use the fact of like the composition of bijection is also bijective. So if A has the same cardinality as B, B has the same cardinality as C, then there exists a bijection G. Let's go from A to B. A each goes from B to C, and they have the same, and they will have the same compositions, or like composition of G taken by first taken the G, and then taken a H. They are this is still a bijection, and this bijection, which means it's transfer the set A to C, which is means A has the same cardinality as C, so it is also transactive. And this result proves the function or the equivalence relation is equivalent relation as well. So let's see some examples about cardinality and its property. So for example, it's like let S be a cis set of Royal Albert Hall, which is a very famous music hall in London, Great Britain. And a seat set, which means a set of seats, a set of total seats in that music hall. And PB is people set, which means a set of all people who will sit in the hall. And if S has the same cardinality as B, then there exists a seat for all people belongs to P, and there doesn't exist a seat to be empty. Give all the people sit down. So which means like so this statement is like that. So if the number of people and number of seats they have the same number, then what happens is like we cannot find an empty seat when all the people sit down. Okay, and if S is not equal to B, not have the same cardinality as P, then there are two cases. Like the first one is too many people, which means like this is P, this is S. If there are too many people, there's 30 people, there's only 2 seats. And there's no function from P to S which is injective, because it must reaches two elements to reach one element by the previous theorem from the last lecture. So too many people, there's no injection. Or if there are too many seeds, what about like there's 3 seeds, but only 2 people, what will happen? It's like it cannot be surjective because this element used to map this element used to map this one, and the remaining more seed is not reached by the function f. So it's not surjective. So there's 2 cases in this case. So this is a very live example. And let's see another example, which is mathematics. Let's say X is a set with 6 elements and A is a set with 4 elements and a subset of X. So X is a set with 6 elements. And A is a subset of it, like let's say it's a 4 subset of element, which is this is A, and the entire set is called X. And B is also a subset of X and has 2 elements. So probably this is equal to B. So in this case, the maximum collection of sets satisfied A's definition is equal to the maximum collection of sets satisfy B's condition. So why this is true? Because if we use the X as our unit set, then B can be written as A's composition because B is all of the elements except that is in A. So like B, A goes to B is equal to A goes to A complement, which is a bijection because each complement is associated with only one set, which is the original set. Okay, and this theorem, this fact can be general to more general case like A has well, let's say X have 10 elements, A have 7 elements, B have 3 elements. If the cardinality of B adding A is equal to X, then this statement like a subset and the maximum collection satisfy A and B, they are the same, is always true. All right, so let's see one core definition here, which gives our a very important conclusion, which means like the set of all real numbers can have the same cardinality as all of the open intervals. So open intervals, we might not see this definition before, but we are just denote it here. Like an open interval from A to B is all of the elements in the real number that is greater than A and smaller than B. So we can define a function f going from in open interval AB and takes from open interval AB and goes to open interval 0, 1. And this is our functions operation system. It takes x to x minus a divided by b minus a, which provide us a sense of like it's a transformation, and the transformation, the map is like shrinkage of the of BA into some very small, very limited area. Okay, and let's say if x1, x2 belongs to the original set here, and x1 smaller than x2, which means like x1 is not equal to x2. In this case, fx1 is equal to this one, and it's smaller than this one because x1, if it's belong to this set, is greater than a and greater than x2. So this is positive, this is positive, smaller than b. So this is positive, positive, this is positive, positive. So we just compare x1 minus a. This is shorter than x2 minus a. So so in this case we say it's smaller. So the fx is also not the same. So it is injective one because it's for all statement here. And also from another fact, like for all of the x3 belongs to the codomain 0, 1. There exists a inverse function of f which takes which have this operation rule as a plus x3 times b minus a. Then this element belongs to the domain, such that every element is reached by the function. So how can we say that is f inverse x3 taken by f is we can write this step, and it's reduced to x3, which means like all of the elements x3 in this one is being reached from at least one element here, which is surjective. So the function is bijective. And by our definition of equipotence, then I think open interval going from A to B has the same cardinality as the set as the open interval going from 0 to 1. And 0 to 1 is a fixed one, but A and B is not fixed, which means like which we can say all of the numbers, all of the open interval, they have the same cardinality as the open interval 0, 1. So graphically we can draw something like that. A and B is very large, but they always can shrink to each element closer and closer to a very short open interval going from 0 to 1. But in some cases, it can be opposite. If AB is even shorter, then what happens is like they are diverse into 0, 1. It's not shrink, but diverse. But 0, 1 serve as a standard set to compare the cardinality across all of the open intervals in real numbers. Okay, and what conclusion we can make here is because all of the A, B, C, D in R with A smaller than B, C smaller than D, and if the open interval going from A to B has the same cardinality as the interval going from 0 to 1, then and C to D is also have the same cardinality as the interval going from 0 to 1. This is because C, D, A, B, they are all general numbers, which is proved by the previous case. And then this statement is also true. And we can also denote as the negative A goes to infinity, which means A goes to negative infinity, and B gradually approaches infinity. Then what happened? And then this set becomes R, because R is the set going from it's an open interval going from negative infinity to positive infinity. We can for now we can view R as this system as well, which is equal to any open set goes from C to D, and C is smaller than D. So this is a very important finding. All of the open interval with length unknown, maybe it's 1, maybe it's 100, maybe it's 1 billion, but they all have the same cardinality. And this probably means like R is very dense, it's a very dense system, and it's an infinite set system. Okay. And for now, let's take some notations. So N0 is equal to empty set. And we denote NN, capital NN. This one we say is all of the elements belongs to the natural number, but is smaller or equal to n. For example, we say like N0 can also be defined in this way because it's smaller or equal to 0, which is impossible, so it's empty. And N1 is 1 because 1 is the only element in natural number which is smaller or equal to 1. And N2 is equal to 1, 2, and 3 is equal to 1, 2, 3. The set 1, 2, 3. and maybe n5 is equal to set of 1, 2, 3, 4, 5. And this is our definition here for what is n capital N. And there's a fact like if m and n is belongs to a natural number and m is greater or equal to n, then Nn is a subset of Nm. Okay, and we define two important definition here as well. One is called a finite set, another is infinite set. And finite set is what is a finite set? Finite set is a set S. If it's empty or it has the same cardinality with Nn with some n in the natural number. And infinite set is if a set is not finite, then it's infinite. Or we say for all of the n n with for all of the n belongs to set zero set union with n as is not equivalent to n for all n here. So this is the definition of an infinite set. And later we'll find out, like maybe in the next lecture we'll find out the infinite set is can be also divided into countable and uncountable set. And that is maybe the first time that you saw infinite set can have different levels of cardinality as well. Okay, so the notation probably I already used before, but notation is defined as it's like an absolute value, but if it's a absolute value surrounded by a set, especially by a capital letter instead of number, it means the cardinality of a set. So A is, if A has the same cardinality as N, which is the set like as defined before from 1, 2, and goes to N. And this means like the cardinality of A is equal to N, which makes sense because they have N elements inside it. So if A is an empty set, then its cardinality is 0. Okay, let's see a theorem. So this theorem is said like if m and n, it belongs to a natural number with n greater than n, then what happens is like the cardinality of A, if cardinality of A is equal to n, and cardinality of B is equal to n, then A is not equipotent to B. Or if if the cardinality of A is n, then the cardinality of A cannot be m. So this might seem very intuitive, like this is common sense, because two set, if they doesn't have the same number of elements inside or their size different, they cannot have the same size. It's just like we define it twice with the opposite definition, things like that. And this is also true because we count one set with n elements. How can we count another time with m element which is not equal to n as more than n? So this is very interesting. It can proved by a way we call it like through mathematical induction, because in this way n is greater than m, so we just need to show n is not equipotent to nm. We just want to show this is true, which means there's no bijection from nn to nm. So we can prove this foundation as well. And this is mainly because like the cardinality of A is equal to n and the cardinality of B is equal to m. So we can say A has the same cardinality as nn, which is not have the same cardinality as nm. It has the same cardinality as B. So we want to show it's not equivalent. We can use the transitive property of the equipotence relation and just to block it in the middle. So which means we want to show this one here. Okay, so what can we do if we want to use a proof by mathematical induction? So first we give a base case which is n equal to 1, m equal to 0, then nm is empty and doesn't have a bijective function going from a set has one element and the element just disappeared after the function, which is impossible. So in this case, there doesn't exist a function. So it doesn't exist a bijection function going from n1 to n0. And in that case, it's like we want n to be k plus 1 and we want m to be k. And here it's like there doesn't have a bijection going from nk plus 1 to nk. And want to find out nk plus 2 and nk plus 1 also doesn't have a bijection between them. And this is very easy to prove because we can say there's a function going from, because what's nk plus 2 greater than nk plus 1 is there, maybe there's some element element B, a new element B inside it, A and B. So here it contains A, here it contains B, which is growing from the original set. And in this case, we can say, A is, let's say, A must matches, like A must going from A to B, or if A is not reach B from nk plus 2, then in this case, like F is not bijective because F is not bijective because if A doesn't reach B, then B is remained. It's remained. So A cannot goes to, so it's not surjective. B is not reached. It's not surjective, not bijective. So this is how we prove it. And we can do another layer of bijection because here is like the n is equal to n plus 1. It's always going this form. How about this is serve as a base case of another layer of mathematical induction? What about n is equal to n plus 1 and then n plus 2, n equal to n plus 3, and maybe n equal to, if n equal to n plus k, and it is always remains true, then n equal to n plus k plus 1 will always remains true. And we want to show this layer as another layer of mathematical induction. And probably we can have a understanding of this one. And maybe it's a good exercise for you to do here. Okay. And very interesting principle is called a pigeonhole principle. So this principle, we can first see what's the intuition for that. It's like if n pigeons fly into n pigeonholes and n is greater than n, then some pigeonhole must at least have 2 pigeons to fly in. So let's say there's more pigeonhole than, if there's more pigeonhole than pigeons, then there must be one pigeonhole that has no pigeons to fly back, which is like another version of it. But there's imagine there's 10 pigeons fly into 8 pigeonholes. Then what happens, like the first 8 fly in and the 2 remaining must share the hole with the already existing 8 pigeons. So this is what it said. And formally and mathematically, it is defined as if 2 non-empty finite set AB with A's cardinality is greater than B's cardinality, then there doesn't exist an injection from A to B. Or like for all of the function goes from A to B, there exists one element in B such that 2 not equal element in A goes from taken by mapped by the function f, and they have the same value. So which means it's not injection here. This is the pigeonhole principle, and this principle is super effective in some theorem, which we'll see in a while. So the proving process, I would say the proving process is very I think you can understand it easily by yourself. Um, it uses the previous theorem, like if A is not doesn't have the same cardinality as B, then there's not an injection from A to B. So with this fact, we can find out all element A belongs to set A uh, must taken by the set F. And because A and B are finite, we can write them out and write them in a form like that, which like it goes around A M because N is larger than M. There's some elements remaining here, and B is F A1, F A2, F A M. And for every element AI with I greater than M, which means like the I is taken value from here, and it must be mapped to some AJ with J goes from 1 to M. So FAJ has two pre-images here. So one is AI, another is AJ, and they're not equal. So which means like these two pigeons, which are different pigeon, must fly into the same hole here. So this is the pigeonhole theorem. I think the most important theorem in cardinality study. So let's see one example. If there's 11 integers and there's only 2 integers whose difference is divisible by 10. This is a true statement because we can say what means like 2 integers difference is divisible by 10, which means their the right hand digit is the same, like 51 and 31, their difference 20, and they have the same right hand digit 1. What about 43 and 41? Their difference is 2, which is not divided because their right hand image is not the same. It's 3 and 1, right? So if we want to make sure their right hand integer, if they're the same, then their difference is divisible by 10. So let A be the 11 integers A1 to A11, and B is the possible right-hand digit, which go from 0, 1, 2, 3, 4 to 9. And by the pigeonhole principle, we can say there exists, by the pigeonhole principle, B is the set of pigeonholes, and A is a set of pigeons, and A has greater cardinality than B. So there exists an element in B which has two elements in A that mapped by the function f to have the same image in B. So there exists one x. Probably we can say the example 2 here, and there's A2 and A11 goes to 2. So their right hand integer is the same. So their difference is divisible by 10. All right, and there's 3 images. Three theorems we'll see. And the first theorem is like every subset of finite set n is finite. So if n is finite already, and A is a subset of it, and this is a straight subset of it, then the cardinality of A is countable. Is calculable. It can be said it's an M, and M is smaller than N. So in this case, we say A has the same cardinality as an M, which is like this one is like have the smaller cardinality as N, and N is what we define as a finite set here. And another very similar theorem is this one. Is every set containing an infinite set is infinite. And just to see here, previously this one, you can, I will pause the proof for 5 seconds and you can capture it to view later. All right. And here, how we can write this one is like for all A, which is a subset of B, and B is finite, then B is finite. Let's say finite. It means A is finite. Right. This is what we define here. And this is the same statement as the theorem. And we prove it is correctness. And here, what's like every set containing an infinite set is infinite, which means like for all of the set B, which is containing some infinite set A. So A is infinite. It means B is infinite. It's just like it's a contrapositive of the statement. B is finite goes to A is finite. So this one is true. It's contrapositive statement must also be true. So we prove like every set containing an infinite set is also infinite. And this is very intuitive. Like, for example, this is an infinite set. It's very large. It's infinite. And another set which is containing this infinite set is even larger, and it must also be infinite because by intuitively thinking like finite is smaller than infinite. And the last theorem we'll see today is the set of natural number n is infinite, which means like the natural number is infinite. And it's not a very big set by our side before. Integer is larger. Integers containing natural numbers. Rational numbers containing integers and real numbers containing the rational numbers. Complex number containing the real numbers, also containing the natural numbers. So if the set of natural number is infinite, then all of those set of numbers is infinite. And we can use a proof by contradiction strategy here. So suppose n is finite, then there exists an n belongs to set n, such that it's a bijection. This is by the definition of like a finite set, of a set with finite cardinality. So for all of n equals to the, for all of n belongs to set natural numbers, there exists m belongs to natural numbers such that m is greater than n. So which means like the cardinality of nm is greater than the cardinality of nn. And by the pigeonhole principle, there doesn't exist a injection G going from nm to nn with nm like nm not in the set strictly is a strict subset of n. So there's no injection H from n to nm. And in this case, there's no bijection U from n to nn. Because like if you take n to nm, not a bijection, and nm to n, not a bijection, and there must be some like must be either 2 belongs to 1, and this is also taken to some end, or it just disappear. It doesn't have subjective. So 2 not bijective function comes in with together is not a bijective function as well. And this is a contradiction to 1. So and it's a infinite set. Okay. Okay, and we can introduce another definition in the last was additional rule. So additional rule is like if A, B are disjoint finite sets, then A union with B is finite. And the cardinality of A union with B is equal to cardinality of A plus cardinality of B. Okay, and that's the additional rule, which means like the union of two sets, if they're disjoint, their cardinality is addable. So that's the lecture for today.